Hello, I'm Zhongtao Wang. Today I'll present ChronoGS, our work on disentangling what stays the same and what changes in multi-temporal 3D scenes. Let's begin with the introduction. In practice, capturing images of the same scene across different time periods is very common. For example, here are aerial captures of the same location in different years. These multi-period images give us complementary data, opportunities for fusion-based reconstruction, and a record of dynamic evolution. However, scenes often change significantly across these periods, both in geometry and in appearance, so existing reconstruction methods break down. To address this, we propose ChronoGS. Next, two preliminaries our method builds on. 3D Gaussian splatting fits a scene with a large set of Gaussian ellipsoids. Image loss gradients optimize each ellipsoid's shape, position, and total count, yielding a real-time renderable representation. ScaffoldGS introduces anchor points that store learnable features. A global MLP decodes these features into Gaussians for rendering. The image loss then jointly optimizes anchor placement, anchor features, and MLP parameters. Now let's walk through our method. ChronoGS disentangles invariants from changes over time. Concretely, we use a shared anchor-based representation to capture the stable scene structure and condition the anchor features on the target time period to represent period-specific changes. The shared representation lets observations from different periods support each other, while the temporal conditioning allows the decoded Gaussians to adapt their geometry and appearance for each period. This lets us consistently reconstruct multi-period captures even with geometric and appearance changes, and synthesize plausible intermediate states between adjacent periods. First, how do we model geometric changes? Our answer is to naturally use opacity. After temporal modulation of the anchor features, if the MLP decoded opacity drops below 0, the anchor is treated as inactive in that period. This elegantly captures the appearance and disappearance of structures over time. Why not just train one separate model per period? Our answer is that joint training across all periods fuses view information together, yielding better geometry, while saving both compute and storage compared with independent per-period models. Now let's introduce our dataset, ChronoScene. ChronoScene draws from two sources. The first is a set of PKU aerial captures from 2016, 2023, and 2024. The second is synthetic scenes built on Matrix City and rendered with the UE5 engine, which gives us controllable ground truth. Altogether, ChronoScene covers 12 scenes spanning both real and synthetic data, organized into 42 subscenes. Each scene period can also be reconstructed as a standalone subscene. In total, the dataset contains 8,891 images. Here is a visual overview of the dataset statistics across scenes. Some example from our real-world aerial captures across different years, and more examples showing the diversity in geometry within ChronoScene. Now to the experiments. Quantitatively, our method achieves reconstruction quality far better than existing approaches across every metric. Qualitatively, our renderings are sharper and stay consistent across periods, while baselines blur or hallucinate. Importantly, our method also produces more plausible intermediate states when interpolating between adjacent time periods, which baselines fail to do. Here is a video comparison against vanilla 3D Gaussian splatting. Ours, on the right, is markedly cleaner. Compared with ScaffoldGS, our reconstruction preserves details across periods that the baseline averages away. Against 4D Gaussian splatting, our results show stronger temporal consistency, without the ghosting artifacts. And here is a comparison with real-time 4DGS on a street scene. Our renderings stay sharp throughout. Coming back to, why not train one model per period? Our results confirm that joint training fuses cross-period view information into better quality, while also being more efficient in both compute and storage. Our ablation study confirms each design choice contributes meaningfully. Removing the temporal modulation or the opacity gating noticeably degrades the reconstruction, validating our design. Finally, the conclusion. To summarize, we studied an important problem that had not been systematically explored, built a new dataset that makes the problem quantitatively studyable, and proposed a simple yet effective method to solve it. Our work is a CVPR26 highlight. Thank you for your attention.